All right, hello everyone. This is lesson 3 of Unit 4. All right, so in our previous video, we had taken a look at a bit of a review in exponential functions from earlier in the year. And now we start to ask the question, well, what else do we know about those exponential functions? Well, now what we can do is put together the information that we got from our last unit with rational exponents, and we could start thinking about, well, are there any situations where we can write an exponential function where, you may have, step 0, step 1, step 2, step 3, but are some functions defined at half steps or other non-whole number steps? Like one example that we did earlier is when we cut a piece of paper. And if we cut a piece of paper, we cut like a fourth of it off. But then three-fourths of it remain, but we can only make one cut, two cuts, three cuts, four cuts. So a situation like that, we don't have to worry about non-whole numbers. But what if we have a situation where, say, a bacteria grows, right? And let's say you have a bacteria and, it starts at a population of, say, 1,000, right? You have 1,000 bacteria, and that 1,000 bacteria doubles, every day. And then, after one day you have 2,000. Then after um, 2 days you have another 4,000. So at day zero, you have 1,000. At day one, you have 2,000. At day two, you'd have 4,000, and so on and so forth. But now, what happens if you have, say, you take all these measurements at 8 a.m. each day so that they're exactly 24 hours apart? So you have 1,000 bacteria at 8 a.m. when you start. One day later at 8 a.m. again, 2,000. 2 days later at 8 a.m., you have 4,000. We use 8 a.m. because it doubles every day. So we're going to say that it's exactly one day has passed. But what happens if you have, say, you want to measure 8 p.m.? Well, what happens in that case? Well, how many days have elapsed since you started? Well, it's still on day zero, but it's 8 p.m., so it's 12 hours later. So half a day has elapsed. So I guess the question is, like, if half a day's elapsed, does that mean it's 1,500? So are there 1,500 bacteria? No, there aren't. And that's because one thing we know about bacteria and anything that's exponential is the more you have, the more it's going to grow. And that's going to be the whole purpose over the next few lessons, is the major understanding that for an exponential function, the more you have, the more it grows. So we can't say 1,500 because the growth won't be linear. We're going to have more of a case where, at 1,000, you may have, you know, extra bacteria every so often, but then once you get those extra bacteria are then going to create more extra bacteria, causing the growth to increase. All right, let's get right down to it. Okay, so let's, a bit of a warm up here. Select all solutions to the equation x times x equals 5. Okay, well, x times x, so x squared. If I were to rewrite this, I would say x squared equals 5, right? Well, what number multiplied by itself gives you 5? Well, looks like that's going to be x equals plus or minus the root of 5, right? And so we want to find all the expressions that match that. Not that. That one works. D works. 5 halves, nope. Root 5 over 2, nope. Square root of 25, well, that is 5, so all good. Looks like it's just b and d here. Okay, what about the next one? What about p times p times p equals 10? P to the third power equals 10? Okay, so to solve that equation, we would take the cube root of both sides. And p equals the cube root of 10. Well, is there a plus or minus sign here? No, because remember, cubes, when you raise a positive to the third power, it's positive. Negative to the third power is negative. So we don't have to worry about all the extra pluses and minuses here. So we just need to find every expression that matches the cube root of 10. Well, E matches 1/3 times the square root of 10. Nope, not F. Any of these with the square root of 10, B's out, D's out. C is also out. But 10 to the 1/3 power. Yes. Okay. So one of the big things that we did a few lessons ago, that's going to come up big in this unit, is the fact that these two are equivalent, and that really the nth root of any number is going to equal a to the 1 over n power. That's going to come back because of this situation here. So what this means is that this number multiplied by itself 3 times gets us 10. All right. So let's take a look. In 1840, the population of Florida was about 54,500. Between 1840 and 1860, the population grew exponentially, increasing by about 60% each decade. Okay, that's a lot. Yeah, Florida grew because, well, back then, Florida had very few people. Imagine the entire state of Florida having only 50,000 people. Um, that's about the population of Ellington and some of the surrounding towns. But picture that, and taking up the entirety of the state of Florida. It's pretty well spread out. A lot of it was swampland. Okay, so let's find the population in 1850 and 1860. So when something increases by 60%, what does that mean? Oops. So an increase of 60%. So what does that mean that we would, because remember with exponential functions, the main operation was we're going to multiply. So how do we increase something by 60%? Well, 60% is 0.6 as a decimal, but then at 60%, we are going to not use 0.6, but 1.6. What does the 1 represent? The 1 represents the fact that we have the original population plus the 60%. This is our growth factor. You might remember doing growth factor way back in Unit 1. Okay, so now let's take a look. Find the population in 18. So in 1840, we know we had 54,500. In 1850, we're going to multiply by 1.6. Let's find that out. Bring that back. Okay, calculator's going to load. Let's try to load. There it is. Okay, perfect. So we're going to do 54,500. And we're going to multiply by 1.6. That gets us 87,200. And then we multiply that by 1.6. 139,520. In 1860. Okay, so the population is a function f of the number of decades d. So could we write this as a function? Well, if you remember, the way that this is going to work is you are going to have the base value, 54,500. But what are we multiplying by? 1.6. And we're going to do it as many times as necessary, and the number of times necessary is that d. And that's the number of decades after 1840. So at 1840, you plug 0 in for d, and you get an answer of 54,500. So here's an interesting question. What happens if we tried to apply that for now? So what if we did 2020? How many decades would that be? That would be, well, let's see, 1840 to 2020. That would be 18 decades. So let's try it out. Let's see what happens. So if I do 54,500 times 1.6 exponent 18, and I get 257 million. Does Florida have a population of 257 million? No, that's like 3/4 of the United States. No, Florida has about a tenth of that. So what does that mean? It means that, well, this 60%, I guess it hasn't held steady the whole time. There's only 60% in this particular range. Outside of this range, the growth rate was some other different number. Looks like a lot less. Okay, but now, what happens if we try to use a decimal, like 0.5? What does 0.5 mean in this situation? Okay, well, again, what does that value represent? 0.5 is a measure of what thing? It's a measure of d, and d was decades. So d equals 0.5 decades. Now, what's half of a decade? 5 years since 1840. That must mean it's the population in the year 1845. All right. So now what we're going to do is we can graph the function using decimals and estimate the value. Now, I don't think we actually have to do that here. You can, but for the sake of um, argument, we can still use the same function. And so I'm going to actually go ahead and do that. And I can use the same function, and I could do 0.5. And that is 68,937. Now, does that number make sense? Now there's 0.65, but really we're not going to count the fractions of a person. Okay, does that number make sense? Well, that number is certainly in between 54.5 and 87. So that number makes sense because it's in that correct range. Just remember, it won't be halfway through that range simply because of the fact that we're not dealing in a linear growth. We're not going to suggest that any part of this is linear. Um, that number is going to be slightly lower than half because um, then creating the new people will then create more new people and it will compensate. Okay, so 68,937, but let's look at that. Okay? Let's look at the expression I used to calculate that. I did 54,500 times 1.6 to the 0.5 because I did half a decade, right? But what does 0.5 represent? A power of a half is the same thing as the square root. And so what I've actually ended up doing is I did 54,500 times the square root of 1.6. And that gets me the same answer. Now the question is, why does it work? It works because what we're doing is we're splitting the 60% growth into two parts. We're splitting it into, so a 60% growth, so we're splitting that 1.6 growth. And we're splitting it into two parts. But we're not splitting it into 0.8 and 0.8. Because yes, I know they add to 1.6, but remember, exponential functions are not built on addition. They're built on multiplication. So we want to know what two numbers multiply to give us 1.6, and it's the square root. Because if you think about it, what we are doing is we are applying a smaller growth rate more often. Basically, a half of a growth rate, well, not, I can't say half, but we're applying a smaller growth rate twice as often. So we have to split this into two smaller multiplication factors, which is why we use a square root instead of cutting it in half. And that's the cause of the difference that we noticed before. Okay, so now that we understand that, can we generalize this to other years? Like, can we find the population in 1858? Well, sure. Again, 1858. So if we think about it, how many years is that? Okay. So 1840 to 1858 is equal to 18 years. But what is that in decades? My function was written in terms of decades, 1.8 decades. So now I can do 54,500 times 1.6 to the 1.8 power. And I can do that. And let's go back and do it. 127,002. And does that number make sense? It should be a little bit lower than the value for 1860. And it is. It's a bit lower than the 1860 value. So the number is on par with that. Okay. Now in this particular case, translating that into a root is going to be a little bit harder. Um, so that's something that we have to kind of watch out for. Over the next few units, or a few lessons, we're gonna take a look at how to kind of think about those as, possibly being a correct analysis as well. Okay. So what do these mean? So what we looked at is, remember, D was decades. So we had 0.5 decades after 1840, 1.8 decades after 1840. But we know that a decade is 10 years. And so we know that we had 5 years, 18 years. Okay. And so now we can kind of comparing all these values and putting it all together. Now we have an understanding, right? So time is terms of decades. So let's fill everything in now. The population that we had before, it was going to be 54,500 times 1.6 to the 0.5. And that number was what, 60 something thousand? 68.9. Oops. 68,937. And again, that makes sense. And then finally here, 54,500 times 1.6 to the 1.8 power. And now what we're going to have is, what is that number? 120. It was what, 127,002. And again, that's in line because that follows with the pattern of the numbers that we see. So what this just goes to show you is that exponents that are decimals can certainly be well defined in much the same way that whole numbers can. And they represent the same thing, but they represent when the quantity of that x variable or that t variable, whatever, can be broken down into smaller pieces. And that we can calculate what happens, like if a function is written in terms of days, like what happens if we break it down into parts of a day, minutes, hours, seconds, things like that. Okay, here's another graph. The amount of medicine in the bloodstream of a patient decreased exponentially. H hours after an injection is given. So when he gets the shot, he has 12, 12 units of this medicine. But after an hour, he's down to 0.75. Ooh, okay. It's a quick disappearing medicine. Hey, sometimes medicine's like that. So, what does 1/3 represent? So, use the graph to estimate 1/3. And what does it mean? So, let's find where 1/3 is on this graph, right? So, 1/3. So let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 lines. So 1/3 is going to be 1, 2, 3, 4 lines. So here's 1/3 right here. Okay, so what does that mean? Well, that's 1/3 of an hour, right? So after 1/3 of an hour, 20 minutes, this is going to tell us how much medicine is left in his body. And it looks like it's slightly less than 5. So after 1/3 hours, there's less than 5 units of medicine. So now, can we find that as an equation? Okay. Well, this is a pretty steep drop. If we go from 12 to 0.75, okay. So all we have to do is remember, how do you find a growth factor? The easiest way to find a growth factor is second term divided by first term. So in this particular case, we're going to do 0.75 divided by 12, and that's going to be kind of small. 0.0625. And so that's going to be my growth factor. Now this time I'm not going to put a 1 in front of it. Why not? Because the amount of medicine is getting smaller. So I want to make sure that my growth factor is less than 1. So I'm going to say that f of t equals, it could be h, equals, maybe I'll do h instead because it's specifically going to represent hours, equals, started with 12 units of medicine times 0.0625 to the h power. And yes, that is 1/16th, by the way. So it's 1/16th each time. Okay. So when this happens, now we can use that to model other numbers, right? You can plug in a third, you can plug in a half, um, and we could do all sorts of things like that. After half an hour, this person's only going to have 3 units of medicine in their body. Okay. So here's another function. The graph to the right is the function 2 to the h power. And we can tell it is because you've got the point 0, comma 1, and then you've got 1, comma 2, and then 4, and then the next one would be 8 if the graph kept going. Okay. So what are the coordinates of P? Okay. Well, let's take a look. Remember, we're looking at the xy coordinate here. So it looks like the x value looks like it's 1/4. And then what value is this? Looks like it's a little bigger than 1, right? But how do we find that exact value? So the exact value of that is going to be, well, since this is 2 to the h function, we can just plug 1/4 in for that function, right? So we're going to do 2 to the 1/4 power. So to make this easier, we'll do 0.25. Okay, so the coordinates of this point is going to be 0.25, and then the y coordinate is going to be 2 to the power of 0.25. And so let's find that number, right? 2 exponent 0.25, 1.19. And that makes sense because it's a little higher than 1. So what does this represent? So it's the population of bacteria H hours after being counted. So when the bacteria is counted, right, after a quarter hour, the value is 1.19. But again, what does that mean? 1 represents the original bacteria, right? So it's the original count of bacteria. But it's gone up to 1.19. Now, if we took it all the way to an hour, it's going to double. So 2 represents the fact that it doubled. This must mean 19%. After a quarter hour, 19% growth in bacteria. Same thing for the next one, right? What about what is this one? 1.25. Could we do the same thing? Could we plug that in for 2? For h? Sure. 2 exponent 1.25, 2.37. What about 2.38? We'll do 2.38. So what does that mean? So that actually means that what you have is not just the original bacteria again, because that's the 1. But notice it starts with a 2. So it must mean that the bacteria doubled and an extra 38 on top of it. So it's a growth of, there's a couple ways we can represent this. It's a growth of 138%. Why 138? Because we took off one that represented the original item itself, the original count of bacteria. Um, the other way we can look at it is we can also look at is 2.38 times the count we started with. That's another way that we can look at it too. Both ways are entirely accurate. And so we can now locate points along that entire function. So along that entire function, we can figure out, hey, what happens after 3/4 of an hour? But then we can also say, how long does it take for the bacteria to triple rather than double? So if it takes an hour to double, how long does it take to triple? Just over an hour and a half. And that's going to be a question that we answer later. So the moral of the story here is that exponential functions can be continuous, and we can use any numbers that we'd like to for inputs. And in future lessons, we're going to look at ways that we can kind of rewrite functions making use of different ways to input, non-integers. Okay, a couple practice problems that we can do. All right, veterinarians use different medications to treat fleas and dogs. Once administered, the medicine typically decays exponentially. It's a very common problem, as you can see in other medicine problems. Okay, one treatment decays by half each week. So a dog receives 4 milliliters of medication, and the function um, will give the number of medicine left after W weeks. Okay, so can we find after 1 week, 2 weeks, 3 weeks? Well, sure, right? Well, okay, so it's half each week. So how much is left after 1 week? 2 milliliters. 2 weeks, 1 milliliter. 3 weeks, half a milliliter. And we could keep going. After 4 weeks, it'd be 1/4 of a milliliter, and so on and so forth. After a while, there would be so little of it in the blood that your blood would probably just filter the rest of it out. Okay. Write an expression to represent the amount of medication in its bloodstream one day after it is administered. So, ooh, 1 day. Oh, how do we do that? Well, how many days are in a week? So 1 day equals how much of a week? Equals 1/7 of a week. So that's because the function is in terms of weeks, and the decay here is in terms of weeks. Then the exponent that I use has to represent weeks as well. So I'm going to say, 4 is my starting value with a decay of a half with an exponent of 1/7. And that will be how much will be left after 1 day. What if we wanted to do 4/7? What if we wanted to do 4 times 1/2 to the 4/7? What would that represent? Amount left after 4 days. So again, we always have a way to kind of model based on, based on the decay that's given. We'll figure out what unit of measurement the decay is given, and then any values that we can plug in, like for that variable, we can convert it to the appropriate unit of measurement. I could have given this to you in terms of years. How much is left after 2 years? How much is left after 8 minutes? And we could find all those values. because all we have to do is convert that into how many weeks. But another way that you can handle it is you can also convert the growth factor too. So, like this problem here, it's days, right? So we converted the days into weeks. But what you could also do is take the growth factor, which is written in terms of weeks, and convert that into a growth factor every day. That is something we'll do in the next lesson. All right, guys, I think I'm going to leave it off here. We did a couple example problems. Here's my lesson summary. This kind of goes over a little bit of the summary there. All right, folks, have yourselves a lovely evening, and I will see you soon. Have fun.